Of all the sights the solar system offers, none is more iconic than the rings of Saturn, and yet rings are far from unique to that one planet. A planetary ring is a disk of countless small bodies, each a separate world, in miniature, each on its own independent orbit about the planet, packed so densely and spread so wide that from afar they merge into what looks like a solid sheet. In truth, nothing is solid about them. Saturn's rings are a swarm of numberless, icy particles from grains of frost to boulders the size of houses, all circling in the planet's equatorial plane. All four of the giant planets carry rings, though only Saturn's are bright enough to see through a backyard telescope, and rings have lately been found even around a handful of small, distant bodies far beyond the giants. This chapter asks what rings are made of, how they hold their intricate shape, where they came from, and why the study of them illuminates disks across the whole universe. The first astonishing fact about a ring is its flatness. Saturn's main rings stretch tens of thousands of kilometers from inner to outer edge, yet they are typically only about 10 meters thick, an aspect ratio like a sheet of paper the width of a city. This extreme thinness is a natural consequence of the countless collisions among the particles. Any that strays above or below the plane soon collides and is damped back into it, so the whole swarm settles into a razor-flat disk. And that disk is in a state of ceaseless differential rotation. For a particle nearer, the planet orbits faster than one farther out, exactly as the inner planets circle the Sun faster than the outer ones. The inner edge of the rings therefore laps the outer edge again and again, shearing the disk without end. The deep puzzle of rings is how they keep any sharp structure at all, clean edges, gaps, waves, braids, in the face of that relentless shearing. And the answer in every case is gravity, from the planet, from its moons, and from the particles themselves. The four ring systems could hardly be more different from one another. Saturn's is the giant among them, broad, bright, and massive, built of nearly pure ice and divided into named rings and gaps, the dense B ring, the fainter R and C rings, and the wide dark lane between them called the Cassini division. Jupiter's rings, by contrast, are a gossamer thing, so faint they were unknown until a spacecraft found them, made not of ice boulders, but of fine dust. Uranus wears 13 narrow, coal-dark rings of some unknown sooty material, and Neptune's 5 faint rings hold one of the strangest features in the solar system, bright, curved arcs that occupy only a fraction of their ring's circumference, when by every rule of orbital motion they should long ago have spread evenly all the way around. Each system, as we shall see, is shaped by the same handful of physical processes, acting in different proportions. Why should a planet have rings at all, rather than another moon? The answer lies in a boundary called the Roche limit, named for the astronomer who worked it out in the 19th century. Close to a planet, its gravity pulls appreciably harder on the near side of any small body than on its far side, and this difference, the tidal force, tries to stretch the body apart. Far enough out, a moon's own gravity easily holds it together against that stretching, but inside the Roche limit, the tidal force wins, and loose material can never gather itself into a single body. It is precisely here, inside the Roche limit, that rings live. Saturn's main rings lie just within the distance at which ice could bind into a moon, which is exactly why the ice there has stayed a swarm of separate particles for as long as it has existed, and why the rings end, and the family of regular moons begins, right around that critical radius. The rings are, in a sense, the moon that a planet's tides would not allow to form. That neat picture has lately been complicated in a wonderful way. Since 2013, astronomers watching distant small bodies pass in front of stars have discovered rings where no simple theory said rings could be, not only around a small world called Chariklo that orbits among the giant planets, but around the distant, icy dwarf worlds Haumea and Quaoar, far out beyond Neptune. Quaoar's ring is the great puzzle. It lies well outside that body's Roche limit, in a region where the particles, by the old reckoning, ought to have clumped together into a moon rather than persisting as a ring. The favoured explanations invoke orbital resonances with Quaoar's little moon, or an unusual bounciness in the collisions between particles, either of which could keep the ring stirred up and prevent it from accreting. These discoveries carry a lesson. It is not tides alone that decide whether orbiting debris becomes a ring or a moon, but the whole intricate dance of resonance and collision, and rings, it turns out, are a far more widespread phenomenon than anyone had guessed. Saturn's rings are chemically almost startlingly pure. Spectroscopy, the reading of sunlight reflected off the particles, shows them to be more than 95%, and by some measures more than 98% crystalline water ice, with less than 1 part in 100 of anything else. that anything else is a reddish, sooty pollutant, a mixture of rock, carbon-rich organic matter, and perhaps compounds whose faint tint varies from ring to ring. This near-perfect cleanliness is itself a profound clue, for the rings are constantly rained upon by micrometeoroids, tiny dark specks of interplanetary dust, and over the 4.5 billion years of the solar system's life, that steady grime should long since have darkened them far more than we see. Either the rings are somehow cleaning themselves, or, the interpretation now gaining ground, they are far younger than the planet they adorn. The very brightness of the rings, in other words, may be telling us that they are a recent addition to Saturn, and not an ancient one. The particles themselves span an enormous range of sizes, from specks a centimetre across up to loose boulders some 10 metres wide, and their sizes follow a very particular pattern, one common to any population ground down by endless collisions. There are vastly more small particles than large ones in a smooth mathematical cascade, but because a boulder holds so much more material than a grain, it is the rare large particles that carry almost all the mass of the rings, while the innumerable small ones present almost all the surface area. This has a curious and important consequence. When we measure a ring by watching how much starlight it blocks, we are measuring its surface area and so chiefly counting the small grains, while the mass hides in the boulders we can barely detect. The two quantities are almost entirely decoupled, which is why, for decades, no one could weigh Saturn's rings at all merely by looking at them. To find their true mass would require an entirely different method, the measuring of their gravity, and that would have to wait until the very end of the Cassini mission. Though each particle obeys the simple laws of orbital motion, the swarm as a whole behaves like a strange, flattened fluid. The endless grazing collisions between particles on neighbouring orbits give the disk an effective viscosity, an internal friction that slowly spreads it wider and keeps its particles jostling at speeds of mere millimetres per second. And in the densest rings, the particles' own mutual gravity draws them into fleeting, tilted clumps called self-gravity wakes, elongated gravitational knots, a few hundred metres across that continually gather under gravity and are torn apart again by the shearing flow, forming and dissolving with every orbit. These wakes are the very same gravitational instability that, on an unimaginably larger scale, seeds the spiral arms of galaxies. A disk of matter, cool enough and dense enough, spontaneously organizing itself into structure. Saturn's rings let us watch that universal process unfold in miniature, close enough to measure, a galactic drama played out in ice, a few hundred meters at a time. The grandest architecture of the rings, though, is carved by the moons that orbit beyond them, through the mechanism of resonance. Wherever a ring particle's orbital period falls into a simple whole number ratio with a moon's, orbiting exactly twice for each single orbit of the moon, say the moon's gentle gravitational tugs, instead of averaging out, add together in step over and over, building a large effect from many small pushes. At such a resonance, the moon's pull launches a spiral wave through the ring, a tightly wrapping ripple of greater and lesser density spreading outward from the resonant radius. These spiral density waves are more than beautiful. By measuring how tightly a wave winds as it travels, astronomers can read off the local mass of the ring, wave by wave, one of the surest ways to weigh the ring's region by region. And the largest such feature of all, the great Cassini division between the two brightest rings, marks the place where particles orbit twice for every orbit of the moon Mimas, whose repeated resonant tugging has swept that broad lane nearly clear. Other structure is sculpted not from afar, but by little moons embedded right among the rings, or orbiting at their very edges, the shepherd moons. A tiny moon orbiting within a gap holds the gap's edges sharp, its gravity nudging back any particle that drifts in, and a narrow ring can be penned between two such moons, one just inside and one just outside, that together prevent it from spreading. Saturn shows the cleanest examples in the solar system. The little moon pan, orbiting within a gap in the outer rings, keeps that gap open and raises delicate scalloped waves along its edges. The tinier Daphnes in a narrower gap tilts on its orbit and lifts vertical waves on the gap walls that cast shadows hundreds of meters tall. Saturn's narrow, braided outermost ring is penned by a pair of shepherd moons that flank it. And around Uranus, the brightest of the narrow rings is confined, edge and edge, by two little moons whose resonances pin it precisely in place, a beautiful confirmation that this delicate machinery really works. Between the great moons and the smallest particles lies a whole continuous population, and among the most delightful of Cassini's discoveries were the objects that bridge them, the propellers. These are little moonlets, a few tens to a few hundred meters across, too small to sweep a gap fully clear, but big enough to push the surrounding particles aside into a propeller-shaped disturbance, a pair of partial gaps trailing from either side of the moonlet. Millions of them stipple the rings, and they reveal the rings not as a sharp divide between ring and moon, but as a single continuous swarm of bodies of every size. Most remarkably, a few of the largest propellers have been tracked across years, and their orbits have been seen to shift, slightly and unpredictably, as the moonlet trades angular momentum back and forth with the disk around it. This is nothing less than the migration of a small body through a disk, the same process that moves newborn planets through the disks in which they form, caught in the act in miniature, and on a human timescale. The faint, dusty rings of the other giants obey a different set of rules, for their grains are so small that forces beyond gravity take hold of them: the pressure of sunlight, the drag of the planet's plasma, the pull of its magnetic field on charged specks of dust. Such tiny grains are swept away within mere centuries or millennia, far too fast for the rings to be ancient, so they must be constantly resupplied, and they are by micrometeoroids blasting fresh dust off small inner moons. Jupiter's gossamer rings betray their origin plainly. Each extends exactly as far as the orbit of the little moon that feeds it. And Neptune's curious arcs, those bright, incomplete segments that refuse to spread around their ring, are thought to be held in place by resonances with a nearby moon, trapping the dust in stable pockets of longitude. Yet the arcs have shifted and faded since the Voyager spacecraft first saw them, and no model fully accounts for them. They remain one of the genuinely unsolved puzzles of ring dynamics. Saturn holds a dusty puzzle of its own. The spokes, ghostly near-radial streaks, lighter or darker than the ring beneath them, that appear across the broad B-ring, last a few hours and fade. They are clouds of fine dust, no bigger than smoke particles, lifted a little way off the ring plane and held there not by gravity, but by electric charge. The favoured explanation is that a micrometeoroid striking the ring throws up a small cloud of vapour, which sunlight ionizes into a plasma. The plasma charges the dust grains, and electric and magnetic forces lift them clear of the larger particles. Because the spokes are governed by the planet's magnetic field rather than by simple gravity, they behave unlike anything else in the rings, favouring certain radii, appearing chiefly at dawn, and waxing and waning with the Saturnian seasons, most prominent when the sun stands near the ring plane. They are a vivid reminder that even in this vast gravity-ruled system, a component of charged dust plays by its own separate rules. Where the rings came from and how old they are remain among the most fiercely debated questions in planetary science. Two broad stories compete. In the first, the rings are primordial, as old as Saturn itself, formed 4.5 billion years ago from material that lay inside the Roche limit and could never gather into a moon. In the second, they are young, the recent wreckage, within the last few 100 million years, of some catastrophe, a wandering comet or an icy body from the outer solar system that strayed inside the Roche limit and was torn to shreds by Saturn's tides, or a former moon shattered by an impact or an orbital instability. The difference is staggering. In one story, the rings watched the whole history of life on Earth unfold. In the other, they did not yet exist when the dinosaurs walked, and are a fleeting ornament Saturn has worn only for a cosmic eye blink. For decades, the question could not be settled, because it turned on a number no one could measure, the mass of the rings. That number came at last from the final act of the Cassini mission. In 2017, its fuel nearly spent, the spacecraft was sent on a series of 22 daring dives through the narrow gap between the planet and the inner edge of the rings, threading over and over a space just a few thousand kilometers wide. As it did so, the faint gravitational pull of the rings themselves tugged almost imperceptibly on the craft, shifting the pitch of its radio signal, and from that shift the rings could at last be weighed. The answer astonished. The entire ring system amounts to only about 4/10 the mass of Saturn's small moon Mimas, a strikingly slight total, far less than a long-lived, heavily evolved ring should carry, and a low mass points toward youth, for an ancient ring, endlessly gathering the dark infall of space, would by now be both more massive and far dirtier than the bright, slender rings we see. The scale tilted hard toward the young ring story. The pristine, glittering ice reinforces the same conclusion. Careful modelling of how fast the falling dust should darken the rings sets a firm limit on how long they can have been exposed, at most a few 100 million years, and by some accounts as little as 10 to 100 million, Two independent clues, the small mass and the clean ice, thus point the same way, toward rings far younger than their planet. And yet the young ring story has its own difficulty, which keeps the debate alive. To make a ring of ice as substantial as Saturn's, something fairly large must have been shredded inside the Roche limit quite recently, and such an event over the last few 100 million years is improbable, requiring that we happen to live not long after a rare catastrophe. Some researchers therefore still defend an old ring, once far more massive, that has slowly shed and cleaned itself to its present state. The mass and the ice strongly favour youth, but they do not yet close the case, and the origin of Saturn's rings remains genuinely unsettled. Whatever their origin, the rings are not fixed and eternal, they are constantly worked and worn. Their internal friction spreads them steadily wider, while the resonances of the moons resist that spreading at particular radii, holding the structure in tension. Micrometeoroid impacts fling material from one part of the ring to another, blurring some edges and sharpening others, and delivering the slow rain of grime that darkens the ice. Sunlight and plasma pull the smallest grains away. Every process that gives the rings their intricate structure is also, slowly, wearing that structure down, so that the rings we see are not a finished monument, but a fleeting balance, a pattern maintained for a while against the forces that will, in time, erase it. And of all those forces, one drains the rings faster than any other, and gives their story its poignant ending. That force is ring rain. Water molecules and tiny ice grains, prized from the rings by sunlight, by micrometeoroid impacts, and by the planet's plasma, become electrically charged, and once charged they are seized by Saturn's magnetic field and funneled down along its lines into the planet's upper atmosphere, where they fall as an endless drizzle out of the rings and into the sky below. Cassini flew through this in FAL and tasted it directly, and astronomers watching from Earth have mapped where it strikes. The rate is prodigious. Enough water pours from the rings into Saturn to fill an Olympic swimming pool every half hour or so, and Cassini's measurements of the material raining straight down onto the equator suggested the true rate may be higher still. At such a pace, the rings are not merely aging but visibly, measurably draining away. Put the two ends of the story together, and the conclusion is remarkable. If the rings are at most a few 100 million years old, and have at most 100 million or so years left before the rain empties them, then their entire existence, beginning to end, is but a brief flicker in Saturn's 4.5 billion year life. We are, in the most literal sense, living in the age of Saturn's rings. They were not there for most of the planet's history, and they will be gone long before its end, and we happen to look up at just the narrow moment when they blaze in their full glory. It is a humbling thought that the single most beautiful sight in the solar system is a passing thing, and that we, of all the generations that might have lived, are among the few to see it. This special epoch framing rests on the still debated young ring estimates, but the convergence of the evidence, the small mass, the clean ice, the swift measured losses, is what makes it the leading picture today. For all their beauty, the deepest value of the rings may lie in what they teach us about the rest of the universe. Rings are the only astrophysical disks near enough to be seen at the scale of their individual pieces, watched year upon year, and even flown through by a spacecraft, and the physics they display is the physics of every flattened, spinning disk there is. The spiral density waves that the moon's rays in Saturn's rings are, in miniature, the very same waves that sweep through the grand spiral arms of galaxies, and that a newborn planet drives through the disk of gas and dust around its infant star. The gaps that little moonlets clear in the rings are miniature copies of the gaps that forming planets carve in those distant disks, gaps now being photographed around other stars, and the self-gravity wakes are the instability that seeds star formation in the galaxies, caught in the act. In Saturn's rings, processes that elsewhere play out over light years and eons can be measured directly, in ice, over the span of a single mission, and much about the rings remains genuinely unknown, a fact worth stating plainly rather than papering over. The true age and origin of Saturn's rings are not settled. The low mass measured by Cassini leans toward youth but does not prove it. The mechanism that pens Neptune's shifting arcs is still unresolved. The composition of Uranus's dark rings is essentially a mystery, awaiting a spacecraft that has not yet been built. The delicate interplay of gravity and friction in the densest rings is still being worked out in simulation, and the discovery only, in the last decade, of rings around small bodies far outside the Roche limit has opened a whole new field whose theory is barely begun. Far from a solved curiosity, then, Planetary rings remain one of the richest and most instructive systems in all of astronomy, the nearest window we have onto the universal behavior of disks, from the ring around a distant dwarf world to the vast spiral of a galaxy. To understand Saturn's rings is to hold, in a single view, a working model of one of the cosmos's most fundamental shapes.